everything minus minus become plus is 3 sigma A squared is equal to sigma U squared, right? So sigma A is equal to square root of sigma U squared divided by 3. So this is equal, so when you have an expression like this, right? So if you put in 1 on my calculator is doing something weird today. Okay, 1 divided by square root 3 is equal to 0.577 sigma y. Okay, so now this looks familiar, isn't it? Right, this is also equal to 0.577. So for this reason, sigma A is equal to 0.557. Okay, we just derive it out. Now let's consider the stress state. Then what we're going to do is let's consider the stress state along line CD. Okay, so let me copy this whole thing. And do I have space? I do. Okay. So what we're going to do now is we are going to focus the stress state along line CD, which I'm highlighting in blue now. Okay. So along line CD, right? Along line CD, what we can see is that sigma A is equal to minus sigma B, always. Okay. So we also know that sigma A and sigma B are the principal stresses. So in the principal stresses, right, the shear stress is equal to what? 0. Okay. So if we were to plot this out on Mohs circle, okay, so considering Mohs circle now, we know we will have this relationship. Okay. So now we're going to construct Mohs circle. So this is our normal stress. Shear stress element rotate clockwise, anti-clockwise. This is 0. And then we are going to have our okay. So this is our sigma A, and then this is our sigma B stress magnitude. And we know that sigma A is exactly here because the shear stress is equal to 0. Now we draw our Mohs circle. So what we realize from here, right, by constructing this Mohs circle, right, we have to ask ourselves, in what condition, okay, if we look at this considering the mole circle, so in what stress state okay, where stress average will be equal to 0 and right, and stress A is equal to minus stress B, right? So I'm talking about elements now. Okay. So in what stress state? So we have 3 conditions at least. Okay. So condition number 1. What I mean by that is based on our stress state, okay, the mole circle will always look like this. The mole circle, after we plot your stress, the mole circle will always look like this. Okay. So now if we were to draw an element, right, because we are looking at stress state now. So if we have an element, right, if we have just pure shear, right, if we have just pure shear, okay, so for this case, condition number 1 is stress X is equal to stress Y and is equal to 0. Our shear XY is equal to shear YX, and this is positive, right? So when you plot mole circle, right, you will get exactly the same thing that you see on the one that are highlighted in yellow. Okay, so I will just quickly do this. So if this is our X, okay, this is our Y, right? So if I plot mole circle, both of them have 0 normal stresses, right? So I just quickly plot them over here. Right? So our normal stress, shearing stress, rotate clockwise, anti-clockwise. So at point X is rotating anti-clockwise. So this is our point X. This is our point Y. The point Y is rotating clockwise. So when we draw mole circle, right, it looks like this. Okay. Right? Where this is our stress A and this is our stress B. Exactly the same like what we have over here. Okay. Then condition number 2, right, which will exactly have the same, is this combination now. Right? And it's where you have sigma X and you have sigma Y, right? And it's a condition where you have sigma X is equal to minus sigma Y. Shear XY is equal to shear YX and it's equal to 0, right? And then when we plot this out, we are going to get exactly the same. I will show you again. Okay, a small mole circle. So now we know that this is our point X. Over here, this is our point Y. And then we construct mole circle again. Right. Again, over here, this is our stress A. Over here, this is our stress B. Again, you get that same circle, okay? Then condition number 3. I beg you, hold on. I do apologize. I knew something was off when I started writing. I'll sort this out later. Okay, I did not specify a page size and it goes everywhere. My thousand of apologies. And then condition number 3. I'll sort that out later. Okay. Condition number 3. No wonder I feel that the paper is getting there's no limit. Okay. It's where you have sigma xy, and then you have sigma y, and then you have sigma x. So the third condition is where you have sigma x is equal to minus sigma y, shear xy is equal to shear yx, and they are not equal to 0. So for this case, you also get the same mole circle. And let me elaborate. Okay. So this is normal stress, shearing stress, element rotate clockwise, element rotate anti-clockwise. Okay. And then we have our normal stress. Right. This is our normal stress. This is our shearing stress. So this is our sigma x, sigma y, and then we have our shear. Right. We have our shear. Okay. So we know that over here will be our point x. Over here will be our point y. And then when we draw mole circle, it will look like this. So again, we satisfy in this strict condition, right? The stress average is equal to what? Is 0. Okay. So if we were to look at condition number 1, okay. So this is in condition number 1 is what we call pure shear condition. Okay, we call this pure shear condition. So loading, if we were to look at loading, under pure shear condition, which is our condition number 1. Okay, so pure shear is when we have a shaft over here, right? And this is how our load is loaded in torsion. Okay, so torque in X also. Okay, in torsion. So when this is the case, right? Okay, if we were to use when Vomisis, okay, Vomisis will recommend or will calculate a larger applied torque when compared to Tresca. Okay, So if you use von Mises criteria, right, to calculate what is the torque required, okay, to prevent failure,